Let's try to calculate the distance factor of z together. So you see, it will be the shortest distance from z to every possible destination in the network. And in the network, it's very small. Starting from z, there are only two possible destinations, x and y. So we just need to calculate dzx and dzy. Now let's calculate dzx first. According to Bellman-Ford equation, okay, so what we do is to try to find out, okay, through all these neighbors connected to the source, okay, which one leads us to the shortest path to the destination x. Now, in this network, we do have two neighbors, okay, connected to z. So let's try the first neighbor first, which is z. So we'll be using the link cost from the source to the neighbor. So link cost from source to neighbor, z to x being 7. And then based on what the neighbor knows, okay, the shortest distance to the destination. In this case, neighbor is x, destination is also x. Now we look up the table. So dx here being known to z, according to that, dxx is 0. Now the second entry, the second neighbor is y. Okay, so we'll then take link cost from z to y, which is 1, and then based on y knows the best to the destination x. So dyx, okay, is the value we need to add link cost zy to. And according to the table, okay, dy says dyx being 2, therefore 1 plus 2. So going through x, we get a pass. The cost is 7. Going through y, we get a pass that the cost is only 3. Therefore, 3 wins. Okay, so you see here, to go from z to x, the shortest pass distance is 3. And next hop is obviously y. Well, let's calculate the other entry, which is zy. Let me clear the markup first. All right. Okay. Again, according to the Bellman-Ford equation, source is z, and the destination we wish to find out the shortest path cost is y. Yeah. In the Bellman-Ford, we'll try, right, for two different neighbors in this network of z and see which lead us to the shortest path. So let's try the first neighbor here, x. Link cost being 7 again, and then what about dxy? Now let's look up the table. It's dxy, therefore, yeah, the shortest distance is 2. So we ended up adding 7 to 2, which is 9. That doesn't look so good. What about the other neighbor of z? zy is 1 again. What about the shortest distance from y to y? And hey, it's itself, so y to y, the cost is 0. So okay, this other path going through y give us only path cost 1. Therefore, yeah, going through y, this gives us shortest path from z to y. And therefore, we update the entire dv, which is now 310. We can actually continue and calculate what is dy, isn't it? So there are again two entries, yx and yz. Let's calculate yx first. Okay, this time y is the source and destination is x. Again, we need to try through all the neighbors of y. So let's start from x. Okay, so x in the middle, source being y, destination being x. So we go through link yx, which is 2 here, and then find out what is the shortest distance from neighbor x to the destination x. So neighbor and destination happen to be the same node. According to the table, x, yeah, the value is 0. So here, going through neighbor x, ooh, nice. Total cost is 2. The other neighbor, so y's other neighbor is what? Z. So Z in the middle here. Link cost yz 1. What about the shortest distance Z knows to the destination X? So dzx, we'll have to look up the table here. dzx, which says 7. So the best path, okay, going through neighbor Z is unfortunately, costing us 8. So comparing the two, the path going through neighbor X is better. Okay, so y, X, and then reaching X. So total cost 2. So we can now update, dyx to 2. The second entry in the distance vector of y is dyz. Okay, so again, starting from y, going to the final destination z. So starting from y, and this time final destination z. We'll have to try through both neighbors. First neighbor being x, link cost from y to neighbor x is 2. The shortest distance from x to the final destination z, dxz. So let's see, dxz. The entry in the table says 7. Second neighbor being z here, so yz, the link cost is 1. Nice. What about the shortest path from z to the final destination z? It's actually quite straightforward, isn't it? zz, trivially 0. And 9 comparing to 1, which one is shorter? 1 here. And at this point, we can also update the entry dyz. And this is how we come to the distance vector of y. So we now finish deriving all the distance vector tables at time t1. What you see also is this. Look at this. dy and dy. Okay. Between t0 and t1, dy did not change. Therefore, dy here, no y here, does not need to propagate the data. Okay, propagate the vector to no x and no z. While, when x here finds out the dx, which is different, from t0's dx, we'll need to propagate dx to no y as well as no z to calculate the table for t2. Similarly here, z find out the new dz being different from the old dz, we'll need to propagate also. dz to no x and no y. Therefore, the two other nodes can calculate if the dx and dy needs to be changed further.